Hi, my physical science students. This is Chief. Today we study chapter 8, the nuclears. First section we're going to study a very important experiment did 100 years ago. And the name of scientist is Rutherford. Rutherford. Please remember his name. Okay, so here's a picture of atom. You can see that's 1, 2, 3, 4, each individual atoms on this surface of a piece of metal. So how we can see atom? We have equipment called STM, or scanning tunneling microscope. So since 1980s, we can see atom directly. But we studied inside the atom, there are protons, neutrons, and electrons. Can we see them? No, we cannot see them, not until today. But about 100 years ago, Rutherford performed a very important experiment and tell us how inside of atom looks like. That's 1911. Okay, here's the setup. And he used what we call alpha particles. Okay, we're going to study alpha decay later. Basically, alpha particles is positive charge, 2 proton and 2 neutron. So now, when the alpha particles beam strike a target, so the target he used is the gold foil, very thin layer, very thin. So now, when the alpha particles strike on surface, and he used a detector similar to this one, all around a circle, and check which direction you can measure the alpha particles. Okay, what he find? He find most particles just pass through. You're going to find most of them around this area. Let's just say if you have 1,000 of particles, more than 900, 950, 960 going to come right here. Okay, then others just go different angle, You can even find few backside come this direction. So what this tell us? By the way, Rutherford and his students spent 4 years for this experiment. Okay, so here's what happens. Most of them pass. Most of them pass. Some gonna change direction, like this one and that one. Very few change back to this direction and even go 180 degrees. So now from this experiment, Rutherford gave a very important conclusion. See, inside of atoms, mostly is empty space. That's why most particles just pass through. 900, 950 of the 1,000 pass through because the inside is empty. By the way, see, here's the thickness. So what Rutherford uses about 200 atom cross. But because, okay, the nucleus is so small, that's why most particles still pass through. Okay, so now when one alpha particle too close to center, what happens? Okay, so now here's gold. Gold nucleus has 79 positive charge, and the alpha particle has 2. So they're going to repel each other. Most likely, alpha particle going to change direction. So now the experiment results tell us inside atom mostly is empty space. The nucleus is 1,000 times smaller compared to size of atom. we also have equation we can calculate. Give you example. So if size of atom like a football stadium, the nuclear just like one piece of blueberry. Think about how small it is. 10,000 times smaller. So now please remember this important conclusion. The positive charge concentrate in a very small volume at the center. An atom is mostly empty space. There's nothing for most part. So that's very important. So now let's review what we studied before. We studied proton and electrons. Rutherford didn't know there's another particle called neutron until 20 years later. So now here's the okay, three particles. At the center we have proton, neutron together we call nucleus. And proton carry positive charge, neutron carry no charge, and then outside electrons circle the nucleus, carry negative charge, positive charge, negative charge, same number but positive, negative. Now the mass is very important. The mass is very important for nuclear physics because mass and energy are related. Proton, neutron much more heavier compared to electron. Here's the first four atoms in a periodic table. Hydrogen has one proton, one electron. Helium, two proton, two neutron, and two electrons. And this is the lithium. So three proton, four neutron, and three electron. That's the first few elements. And we can study more detail about different elements, their property, when we study chemistry. So now a few important definitions. The elements is the most simple substances. There are about 110 elements in periodic table. Now atomic number. Atomic number is the number of protons of elements. It's a very important number. Now another important definition is the isotopes. Isotopes. So what are the isotopes? The atoms of given elements that have the same number of protons but different number of neutrons. For example, so we have a hydrogen. So all the three are hydrogen family. The first one is ordinary hydrogen. One proton, one electron. And this is the isotope we call deuterium. One proton, one neutron, one electron. Tritium is another isotope. One proton, two neutrons, and one electron. See, they have the same number of protons, but different number of neutrons, 0, 1, and 2. So we call them isotopes. So same proton, different neutron. Now, another important concept we call nucleons. So proton and the neutron all together we call nucleons. This has one nucleons, two nucleons, and three nucleons. Now, next one is nuclide symbol. So nuclide symbol we use for nuclear physics, so we can find information about nuclear. Okay, the symbols like this. You have big letter here, X. X give you the name. So if the H is hydrogen, if O, oxygen, if the HE, like my last name, that's helium. Okay, now the two number one at the bottom on the left side. So Z. This number is the atomic number. Give you a number of protons. Then now the A, okay, the top one, capital A. This number we call mass number. Mass number. This number give you number of nucleons, proton plus neutron. Okay, so now I'll give you two examples. So if I give you a sample like this in the quiz or in the test, what kind of information you can find? So this Cl, and now the number on the left side, the bottom 17, the top 35. So Cl tell the name. By the way, I will give you periodic table, so you can use periodic table in the test. So if you check periodic table, number 17 give you chlorine. Chlorine, that's the name. So now, how many protons? Okay, 17. This number tell you 17 protons. How many neutrons? Because the top number, this one, give you proton plus neutron. So we need to do simple math. 35 minus 17 give you 18. So 17 protons, 18 neutrons, and 35, because totally 35 nucleons, proton, neutron together. Now, second example. Okay, this is the mercury. Again, if you have a periodic table, you check number 80, then you find the name as mercury. So now see the number on the left side, the bottom is 80, tell you 80 protons. The 200 tell you the number of nucleons, so it's 200. So how you can find the neutrons? Because this is a total number, so 200 minus 80 give you 120. That give you number of neutrons. So has 80 proton, 120 neutron, and 200 nucleons. So now, section 3, we're going to study radioactive decay. So if I have a chance, I will give you some demonstration. So now, what is radioactive decay? Scientists find some isotopes are unstable. Unstable. What do you mean unstable? Unstable means they're going to give off released particles of energy automatically. So if some isotopes give off energy of particles, we call they are radioactive. And we call radioactive if they give off particle energies. So now there are totally 6 different decay, but in our textbook, we're going to study 3 of them. 3 important decay. So you should remember their name, what kind of decay, particle energy, and other important information. So now the first one we call alpha decay. Alpha, that's a symbol, alpha, Greek letter, alpha decay. So when alpha decay happens, a nuclear will give off particles called alpha particles. Each particle has 2 protons and 2 neutrons. Look at this figure here. This is before, this is after. What happens? Okay, 1 particle come out. This particle has 2 protons and 2 neutrons, and we call alpha particles. So before and after, the atomic number change. 1 nuclear change to another, because 2 proton less and 2 neutron less. Now the second one we call beta decay. When beta decay happens, you see the electrons are released. So these electrons come from inside nuclear. That's very, very important. From inside. Okay, so what happened is 1 neutron change to a proton. Okay, so now here's the isotope of the hydrogen. Remember, two neutron and one proton. So now, under certain conditions, one neutron switch to proton. See what happens? Now you have two protons. And at the same time, an electron come out. Uh, so simply speaking, alpha decay will give off electrons. Uh, so beta particles are electrons. We call beta particles because from inside nucleus is not from there. Now the third one we call gamma decay. Gamma decay give off gamma particles. Gamma is the symbol. So gamma decay give off not particles but energy. And it's very high frequency, just like X-ray. Before, after nucleus basically same, but the energy reduced. So you're gonna see very high frequency. The frequency is the same or higher than X-ray. And this kind of decay we call gamma decay. And we're going to study, we can also call EM wave photons, wave nature and particle nature. So gamma decay, you can see the photons come out, or you can see EM wave come out, either way, photons or EM wave. So there's three important decay. Alpha gave alpha particles, two proton, two neutron. Beta decay gave beta particles, electrons come out. Now the last one, gamma decay. Gamma decay give off EM waves with very high frequency. But how we can tell which decay happens? Well, we can use magnetic field. We studied this in chapter 6. Remember magnetic field. So electrons are going to change direction inside the magnetic field. Okay, so now if this is a chamber, then decay happens. Okay, you don't know what kind of decay come out. So now, if you have magnetic field, you see the cross, that's magnetic field. Means out paper is the N, inside is S. So like arrow go inside. So now the positive charge, that's alpha decay, will turn to this direction in magnetic field. So now this decay is alpha decay. And that one, because the electrons, beta decay, has negative charge, will go another direction. So you know that's beta decay. It was gamma, because gamma has high frequency radiations, no electric charge, so will not change direction. So you can use magnetic field determine which decay happens. Most isotopes, were light one like hydrogen or helium, were heavy one like uranium. They all decay. They all decay. Now another important concept is we call the penetrating ability of radioactive decay. See this figure first. So we use three. First we use a cardboard, and then after we have aluminum foil, or thin foil. Okay, so now the third one we use a lead, with heavy metal, metal block. So now if you have alpha decay, alpha particles, the cardboard can stop the particles. So we say alpha particle has the least penetrating ability. Now beta particle, which is electrons, can pass cardboard, but you can use aluminum foil to stop. Now the gamma ray is most penetrating. So gamma ray can pass the cardboard, aluminum foil, even lead block. Of course, going to reduce energy. So we say the gamma ray are the most penetrating, and alpha particles are the least penetrating. So we should remember this conclusion. Alpha particle is the least penetrating, gamma ray are most penetrating. Now, next important concept we study in section 4, we call half-life. So what is half-life? What is half-life? The half-life is the time period when half of sample decayed. When 50% of sample decayed, we call the half-life. So half-life is the time when the sample reduced to 50%. Well, when radioactive decay happens, some decay go very fast, some go very slow. For example, radium, the half-life equals 1,600 years, and carbon-14, even longer, close to 6,000 years. Okay, but some of them, like polonium, the half-life very short, 1.8 microseconds. So some radioactive decay go very fast, some go very slow. So now, this section we study the definition of half-life. So I'll give you an example. Suppose we have one piece of radium. Then suppose when time equals 0, so we start radioactive decay. So if we can wait one half-life, which is 1,600 years, what's going to happen? So half the sample going to change to radon, but you still have half left. So the half-life is time when 50% of sample decayed. So now what if we wait a second half-life? So if we wait another 1,600 years, so totally 3,200 years, right? So then what happens? So now this half gonna cut another half. So we're gonna have 1/4 left. So the green part is sample decayed. So another half-life, you have half of this part decayed. Then if we wait another half-life, what happens? Half of this decayed. So you have 1/8 left. So the half-life is time when 50% sample decayed. It doesn't equal half of the whole life. Whole life is infinity. Well, theoretically. So now here I'll give you the definition again. Use a table. Suppose equals, when time equals 0, you have 10 gram of sample radium. So after 1,600 years, what happens? 5 gram left. 5 left. Another half-life, you have 2.5 left. 2.5. Another half-life, you have 1.25 left. So you cut half of the half, then cut again. And we have so many applications for half-life. For example, dating of sample. Suppose you find fossils. You can measure the carbon-14 because after animal died, the decay start. So every half-life is around 6,000 years. The carbon-14 going to reduce to half. So now another 6,000 years reduced to half of the half. 25% left, and so on. So by measure how much carbon-14 left, scientists can estimate the age of fossils. We're going to stop right here for first part of the chapter 8. Thank you.